In this video, we're going to talk about the development of the least squares line equation. So let's say we have random variables x and y, and the joint support we're going to denote by s. Let's consider all lines of the form y equals ax plus b, and basically what we're going to be looking for is somehow what's the line that looks the best as far as an approximation of all of the points in S. So what we mean by this is if we have an ordered pair xy, or x naught, y naught, in the support, let's consider the vertical distance between this point and what would be on the equation of the line. So a point on the line, of course, would be, if I plugged in x naught in here, we would get y naught here. So if this x naught, y naught were on the line, we would get y naught out here. Instead, we would get some y coordinate here. So if we want the vertical distance between those 2 points, we would take the y naught, subtract off what we get when we plugged in x naught into the equation of the line, and take the absolute value since we're looking for distance. All right. So our goal here is to try to minimize this distance over all the points in S. Okay, so what do we mean by minimize in this case? Well, since we're talking about a probability space, if you will, we've got points, each of these points have some associated probability, or at least probability density associated with them. Really what we're looking for is an expected distance, if you will. So we want to try to minimize an expected value of this distance. Now, with this absolute value in here, it makes calculus a little harder as far as differentiation is concerned. Since we're trying to find a minimum, we probably want to differentiate at some point. So rather than looking at minimizing this absolute value of the distance, let's square it so that we can get rid of the absolute value, and then we have a function that's differentiable, and we don't have to worry about any sharp corner type points. So really the function that we want to minimize is this function in terms of the constants a and b of the expected value of the square of y minus ax minus b. All right, so if we want to minimize this function, we need to consider critical points of this function. We find critical points by looking at the partials and finding out where the partials are simultaneously 0. So we take the partial with respect to a, we bring down the 2, differentiate the inside with respect to a, we just get a minus x. So we get that expected value. For b, do the exact same thing, except that when we take the derivative of the inside function, we would get a -1 in that case. Recall that partial derivatives and expected values behave nicely with respect to each other because either we're talking about doing a sum or we're talking about doing an integral, and we can just pass the differential operator in between across those two types of things. So anyway, the important part of that is that derivatives behave nicely with respect to expected value. All right, so now let's solve simultaneously. Here, if I rewrite this expected value equation, or expression I should say, we get expected value of xy. We can break it up over the difference. We could factor out the -2 out in front and divide it through so we can get rid of that -2. We would have an xy, so I need expected value of xy. I would have an expected value of x squared times an a. That's where that's coming from. And I would have an expected value of x times a b. That's where that's coming from. Do the same thing with the second equation. Okay. All right, so I want to solve these simultaneously, so let's eliminate one of the variables. One of the things that I notice is if I multiply the second equation by expected value of x and subtract, the expected value of x, the b terms will go away, and I'll just have something in terms of x, or a, sorry. So first equation would have expected value of xy. The second equation now would have an expected value of x, expected value of y. So when we subtract, we would get those two terms grouped together. First one we have expected value of x squared. Second one we'll have an expected value of x quantity squared. So again, grouping those terms together. And then those with the b's in it would cancel. And we would still have 0 on the right-hand side. Notice this first term now is covariance of xy. Divide out, this is variance of x. So we have covariance of xy over variance of x. Remember, your covariance of xy is the correlation times the product of the standard deviations. So one of the standard deviations will cancel out, and so you'll get rho, the correlation coefficient, times the quotient of standard deviation of x over the standard deviation of y. All right, let's plug this into the second equation and solve for b. When we do that, we'll get b is the mean of y, because that's the expected value of y, minus that rho sigma y over sigma x times the mean of x, because mean of x is expected value of x. Last thing we need to do is make sure we really do have a minimum value of that k of ab. So take the second partials, all 3 second partials that we can have, do the second partial with respect to a, and then with respect to a again, we get 2 times expected value of x squared. The mixed second partial is 2 times expected value of x, and the second partial with respect to b and then with respect to b again gives you 1. You can go back and check those. So now at the point a comma b, for the a and the b value that we found, you do the mixed second partial value squared minus the product of the other second partial terms. We find out that we have a negative number here, because we have negative 2 times the variance. If you factor out a negative 2 here, you'll see that. All right, so since that expression is negative, and since this one is positive, we really do get that that point P that we had is a minimum value. So we get what's referred to as the least squares regression line. Again, the least squares comes from the fact that we're minimizing a square of a distance. When we plug those values in, we'll get y equals the a value times x plus the v value, or rearranging, we can write it as mu sub y plus correlation times the the quotient of the standard deviations times x minus the mean for x. So in particular, notice that the least squares line has to pass through the point that is the mean of x and the mean of y. That's kind of a cool little property. Also, let's figure out what the minimum value of that function k is. So plugging in the value of a and b that we found and simplifying, we get y minus mu sub y minus the slope times x minus mu sub x. If we square out those individual pieces, we will have expected value of y minus mu sub y quantity squared minus, we'll get 2 times the slope times expected value of x minus mu sub x times y minus mu sub y, and then plus this squared, this slope squared, which is here, times the expected value of x minus mu sub x squared. All right, let's look at these 3 expected values that we have. The first one is the variance of y. The second one is the covariance of x and y. The third one is the variance of x. So substituting those 3 values in on the next line. Now let's do some simplifying. Covariance of xy again is rho sigma x sigma y. Over here, the variance of x's cancel. Here, we also get that the standard deviations of x's cancel. So we get 2 rho squared variance of y. And then here we've got a plus rho squared variance of y. So we simplify, we can factor out a variance of y. We get variance of y times 1 minus rho squared. All right, so let's see what this implies. We notice that, again, remember how we defined our function k. It was the expected value of a square of a quantity. That means that k could never be negative, because it's the expected value of a square. Those certainly can't be negative. So we must have that when we take the variance of y and multiply by 1 minus the correlation squared, we have to get a positive or a non-negative number, which then implies then that our correlation coefficient has to be between negative 1 and 1, which is an important property of correlation. Also notice that the closer the correlation gets, the smaller this quantity gets. The closer and closer it gets to 0, which means it's the closer and closer that our values in our support get closer and closer to that line. So if y and x were perfectly correlated, then this variance, the expected value of our difference between those two things would be 0, and we would have those perfectly linearly related then, the y and the x. Also, if you've seen any statistics, you know when we talk about least squares, how good of a fit is relates to that r squared value, or the correlation coefficient squared value. The reason for that is exactly this. When you've got a small correlation, this is closer and closer to what the variance of y is, so that the model really isn't explaining any error because the error in the model is essentially the error in the y. However, when this gets closer and closer to 1, this gets smaller and smaller, your error term gets smaller and smaller, so it starts to explain more and more of the error. So that's why the r squared is used as a percentage, if you will, of the error that is explained by the model. It's this exact expression here.